Very good morning to Sir and my fellow friends. Today, our group is going to present the Smart Home Gardening Monitoring System by Feng Zhao, Li Mingwei, Ke Jian, and me, Leong Yu Sang. So I'm going to talk about the background, the rise of smart home gardening system. Gardening is a popular hobby for connecting with nature. However, smart devices and IoT are changing our daily life. So the sensors and connectivity inside the system enable automation and data-driven decision making. Using smartphone, user can control and monitor plant and soil health remotely. The key components include the sensors for soil moisture, sunlight exposure, and nutrition level, and so on. The real-time data is being processed by intelligent algorithms, and the data can be stored inside the cloud database and used for training the system to make prediction, and so on. The system can detect critical conditions that affect the plant health. So smart home gardening is a natural evolution in cultivating plant at home.
Good afternoon, sir. My name is Li Mingwei, and now I'm going to talk about the history of smart home gardening monitoring system. The first will be origins and evolution. Smart home gardening monitoring system originated from tech and environmental concern, evolving with sensor for plant monitoring. The second will be regulatory standards. Authority established standards balancing innovation and sustainability, focusing on water and pesticide use. The third will be user knowledge challenge. Lack of technical knowledge among users pose a challenge in effective system utilization. The fourth will be regulatory adaptation. Regulation continuously adapt to address data security, connectivity, and ethical data use. The last will be promoting responsibility. Public awareness campaigns and education promote responsible gardening, empowering users for sustainable practice. Next, I will talk about the future trends of smart home gardening monitoring system. So for the first will be the automation for accessibility. Smart home gardening systems are evolving to offer affordable automation, reducing the manual effort and making the gardening accessible to the all. The second will be the privacy and security. Future systems prioritize data encryption, user consent, and secure storage, ensuring the protection of user information. The third will be sustainability and emphasize. Regulation focus on water-saving methods and sustainable material, promoting a environmentally friendly practice. The fourth will be innovative device. New device enhance the effectiveness and productivity, from smart sprinklers to sensor monitoring soil condition and security cameras ensuring the safety. The last will be benefit for user and environmental. Affordable smart system offer a comfort and convenience, minimizing the effort and contributing to cleaner, more connected to the urban environments. That's all for my part. Thank you.
Good morning, sir and everyone. My name is Ke Jian, and today I will present about the problem statement and also the objective for my group. After that, I will also present about my part in the cloud solution, which is the AWS IoT Core. So first, the problem statement of our project is the lack of regulation raises concerns due to the absence of the control environment like greenhouses, and the inaccurate sensor readings or misinterpretation can trigger inappropriate watering or fertilizing. So the homeowners actually is lacking the specialized knowledge in both plant care and also the smart technology. So the objective of this project is we want to develop a low-cost smart home gardening monitoring system so that to help the homeowners to regulate their farms. This system can help homeowners to collect the information about the plants and also the environment such as the humidity, temperature, soil nitrogen content, and others. After collect the information, it will be analyzed and also display, not display, is visualized in the clouds, and homeowners are able to make a decision when they are looking at a visualization about the predicted future humidity and temperature near sensors.
Good morning, sir. My name is Feng Zhao. The following is our system architecture design. First, IoT sensors will capture the country's weather and soil information and send it through the internet into the AWS IoT Core, which connects all the IoT sensors into the cloud. Then, using an AWS Lambda function, the sensor information is retrieved, formatted into CSV files, and stored into an Amazon S3 bucket. At the same time, if the chance of disease in the soil is high during that day, another Lambda function will format a notification to send to the user in order to spur action from them. Next, Amazon Forecast will grab the sensor information in order to forecast future trends of the soil and weather data. The predicted data will then be stored inside another S3 bucket. Amazon Athena will grab the predicted data alongside the user and plant information that is stored in another bucket that is stored beforehand, and using queries, combine them into a single table which combines the predicted information, the user information, and the plant information, which then be passed into Amazon QuickSight in order to perform visualization and analyzation of the data in order to determine critical conditions in the weather or the soil that can harm the user's plants, and to warn users about these potential critical conditions to spur action from the user. This visualization would then be sent to the end user. We will now go on to the demonstration of our AWS solution.
So now I will present about my part in the cloud solution, which is AWS IoT Core. Okay, so this is our groups, the IoT things. We have sensor 1 and also the sensor 2. So if you log into the sensor 1, and there is a certificate ID. This certificate ID is that it can prove that it comes from the Amazon, and also the Amazon can prove the communication from things to the AWS. So if you want to test the IoT things, we can go to the MQTT test clients. Okay, so this is MQTT test client, and it can link the certificate ID to the quotes so that the Amazon can know which one is the certificate ID. So if we now want to test, we can subscribe the topic first. So this is the topic filter, which is sensor 1. I already subscribed just now. So if I click the subscribe, and it will display the message, which is hello from AWS IoT Core console. And after that, we can receive the published information for the quotes, which can show the things that which you have proved that the things actually is already connected to the Amazon. So I will now run the codes. Actually, this is our group coding. And this is the certificate ID. And this is client ID. So after I run the coding, and it will show the connect message. And after that, if I log into the MQTT test client page, and it will show all the information of the plants. After the information of the plant is shown, and another called the lambda function will trigger and take the info of the plant information. Because after it trigger and take the information, it will format to the S3 bucket in a bucket called the plant sensor data. So objective objects will be explained later during the Amazon podcast. So not only this, we are also got another. The lambda function is called disease warning. So the disease warning is about when the plant's information, the disease percentage, one of the plant's information is bigger or equal to the 30, it will send the emergency email to the homeowner's emails.
Now I'll be showing the Amazon forecast of our system. So we are doing barrel pressure forecasting. So here's the place that used to import the data. We have two types of data here, target time series data and related time series data. So basically, target time series data is something that is the target. So we are doing barrel pressure, so our target is barrel pressure. Then related time series data is the data that used to predict the barrel pressure. So next move on will be the predictor. We can train the predictor by using these two type of data. So before we view the predictor, let's talk about the train predictor. We need to key in few things. First one is forecast horizon. This one is basically something that represent how many days that we are going to predict. For example, if 10, then we'll predict the next 10 days. Then because our data set is small, we have only 18 of data sets, so we can only manage to predict the next 2 days. So this one we will key in 2. And this one is quantile. They have 3 quantile here, 0.1, 0.5, and 0.9. So next one, we will view the predictor. So this is our prediction, blood pressure prediction. And now you can see the status active and the forecast time is 0.1, 0.5, and 0.9. This is WAMP and RMSE. And created on 10th of April. So now I will show the data set. Okay, move on to S3. Our data will be stored inside the S3. So here is it. Sorry. I mean, this sensor predict the pressure predict. Then why we have three Excel file? This CSV file here is because we have three sensors. As you can see, this one is the sensor S001, sensor 1. So just now I mentioned we can only predict the next 2 days. So our data is only until 10th of March. So this one I drop the location, and this one is the P10, P50, and P90, the 0.1, 0.5, 0.9. So that's all for me. Thank you.
So now I'm going to talk about the Amazon Athena. For the data such as user and plant, we actually insert in the beginning. But for the predicted data, such as power pressure prediction, we actually insert from the Amazon forecast, as you can see from the screen. So first of all, we will look into the graph parametric predict to take the prediction data. As you can see from the line 11, the location, but actually we take the data from the S3 bucket. So we will look into the power pressure predict row. So as you can see, they got the timing that we actually noted, and the barometric pressure got three different pressure values such as P10, P50, and P90. So after that, we will open the barometric predict to see the data. So actually, you can see that the barometric predict data has been formatted in the clean and more tidy ways. So we add that we got combine all the data so we can see another query to grab all the information. First, we will open the grab branch data. So as you can see, I will open one of the data and preview the table. So here will be the data such as plant ID, withstand drain, the name, and the preferred nitrogen. For the user, actually will be the same. Here got some user information such as user ID, the process sensor, which include the three sensors that the main that we do, and the plants. So next, I will open the graph validated data. We assume that we already combine and format all the data. How we can take out the data? So I will show the table also. So here will be all the data that's stored inside the table. For example, the sensor ID, geolocation, the date, the barometric pressure, humidity, temperature, wind speed, soil nitrogen content, and the DC%. So we actually need to combine all the data. So for the quick set purpose, so we actually generate 4 tables. For the first will be the graph predicted S001, which means that the sensor 1, sensor 2, sensor 3, and the overall prediction data. For the S001, we can open it to see the table. So as you can see, the process sensor is all about the sensor 1. As it's same for the sensor 2. It's so all the same sensor 3. Same, and we will open the overall, which is the analysis data. So it actually involves all the three sensors into one main table, which include all the information such as user ID, the name, the withstand rate, preferred nitrogen, the geolocation, the date, the barometric pressure, humidity, temperature, wind speed, soil nitrogen. So that's all for my part. Thank you.
Finally, for our AWS solution, we use Amazon QuickSight in order to analyze and visualize the predicted data that is obtained from Amazon Forecast in order to show potential critical conditions of the weather and soil that can be dangerous to users' plants. By clicking on New Analysis and importing the data that is obtained from that is queried from Amazon Athena, we are able to create this analysis. So in this analysis, we've imported 4 data sets. The analysis data, which is the combination of all the predicted data, the user data, and the plant data, and S1, S2, and S3 analysis, which is the separation of each sensor in the analysis data. We have 4 total sheets in this analysis. The first sheet shows the user shows which user is close to which sensor for their reference. The second is the weather analysis, which shows the trend, the future trends of the humidity, temperature, and wind speed obtained by Amazon Forecast. Then, by using insights, and by looking at the lowest or highest possible values of humidity, temperature, and wind speed, and determining if the user's plant is able to withstand heavy rain, the QuickSight will tell the user whether or not they need to take action. For example, users near S001 will need to take action around March 31st, while users near S002 and S003 don't need to take any action. For the soil disease percentage, it's about the same, where it shows the future trends of the soil disease in the near each sensor, And then using insights, we'll tell the user whether or not they should take action, whether or not they're near to certain sensors. Finally, for the soil nitrogen content analysis is also nearly the exact same, where it shows the future trends of the soil nitrogen content. Then the insights will try to take the smallest possible value and tell the user whether they need to take action or not, on which day. For example, SO1 is March 18th and SO3 is March 22nd. Then we can publish this analysis, which will show up as the dashboard. And then by sharing this dashboard, we can let users see the analysis themselves. Thank you.